have a lot of individual pieces or one large piece, right? Remember we did that example on the board where I did little pieces of oil and then the one big piece, right? What was the advantageous about having the one big piece? So you had less ordered waters. So entropically, it was more favorable. When we talk about favorable, we talk about our delta G being more negative, right? So you're talking about comparing those two different states now. Remember, this delta is the difference. So you're looking at the difference between those two. Does that help? Other questions for me?
So if it said describe it with a chemical equation, you pretty much just use the Gibbs free energy equation, and then when it says describe its thermodynamics, is that just essentially that the temperature is high, or?
Nope. It's all that you want to do is describe that this is the predominating term.
Okay.
This is what drives this. There's no, for all intents and purposes in this class, there's no enthalpy difference. It's all entropically driven. Because the cost of making and reforming a hydrogen bond is about a -0. So the enthalpy stays pretty much constant. The entropy changes dramatically in those two different scenarios. And that's what drives the delta G to the common. Other questions?
It's on the technical moment where they talked about drawing representation to anti-chemical data and then describing the primary sequence.
Yep, an amphipathic being. So what's amphipathic being? One side is polar, the other side therefore would be non-polar. So if you have anti-parallel, let's say I have this going from N terminus to C terminus here, what's the other straight going? What's over here? This end is N, this term over here is C. Everybody okay with that? So we know how to draw that, so you can just draw something as simple as that. However, what you want to do though is you want to make sure that you have the right R groups in the correct orientation. What do we know about where the R groups point in a beta sheet? They alternate, they go in, out, in, out, in, out, in, out. So if you were to look at the primary sequence of an amphipathic beta sheet, what types of repetitive sequences would you get? Polar, non-polar. So you'd have, I'm just going to abbreviate P and N. It's not, no, I'm not going to do that. That's just one letter code. So actually, yeah, I could P and N, P and N, P and N. Okay? Polar, non-polar, polar, non-polar, polar, non-polar, polar, non-polar, polar, over and over and over again. So you would see in a beta sheet, those one after the other. Does that help? So again, you want to make sure that the face where they're interacting, where there's no water there, that would be your non-polar face. If these two sides are facing water, what would these two sides be? There would be the orientation of the polar residues.
So on an example, you just want us to draw the arrows. Would you want us to put the PNNs?
The polar, non-polar. You should designate sort of what that is,
okay,
or where they would be, where you would find that type of environment. Same thing like when we talked about alpha keratin and things like this. When you have an alpha helix, you have it facing this way. You could have an alpha helix facing this way. You could also have an alpha helix facing this way, right? So here you would have residues maybe 2 and 3 would be on the inside. Here you have 1 and 4 on the inside to keep that phase. Right. Yeah. Did that answer your question? Good.
So if it's a parallel data sheet, would the primary structure of the NEOS sequence look the same as the okay.
It would. Yeah, it still repeats. It's just you would have to go from each N-terminal end into the C-terminal end. That would be the only thing.
As for calculators, are we able to?
Yep, you can bring. I don't care what you bring.
So when you say alternating polar, non-polar, so the non-polar goes inside and then you have a polar one going outside, or what do you mean by that?
Yep, so if you have, like, let's say the plane is here, okay? So that means your R group would face down, the next R group would face up, the next R group would face down, the next one would face up, this way, this way.
Yeah, they're not facing towards each other and away from each other, it's up and down, right?
It's whichever way you want to think about it, because remember so these are alpha carbons, so they're a tetrahedron. So you have two groups that will always be on the plane, whatever that plane is. You have one group going back, one group going forward. So if this is always the group that comes forward, or the R group, if this one's always the R group, it goes, if this is the plane here, one goes back, the next one goes here, the next one goes here, the next one goes here. So it's just that. What? Oh, no, because N is asparagine.
Oh.
N is a non-polar and polar.
Right, but I use the one letter codes for proline, asparagine, proline, asparagine.
Oh.
Yeah. That's how I can use it, because I would put that. So, hang on. 1, 2.
About
about the beta sheet, so there wouldn't, the anti-parallel and parallel, they would just alternate like that, but there's not a difference between, okay.
It would be in the orientation which you start them, right? So if you had two anti-parallels and this one came out, you'd have to say that, well, the C terminal of this matches up with the N terminal of this. Whereas in a parallel, it would be that two N's line up and the two C's line up. So that'd be the only difference, but it'd still be that alternating.
I have a question. Is the anti-parallel, when you talk about the hydrogen bonding that's happening, is that, since the inside says the nonpolar, the hydrogen bonding would only be between the nonpolar R groups on the inside of the beta
No,
sheet?
because the hydrogen bonding is in a different plane, right? So if this is the R group and the H that's there, these other two groups are the carbonyl and the N. So those are in the plane. Yeah. So it's, let's see if I have a, hang on, let me find that for sure. So if you look at this, right? Okay, so here, they're calling this the plane because here's the carbonyl, hydrogen bonded here. This is the alpha carbon, the R group is pointing out or back. And this one, the other, if this R group points this way, this R group points back in, this R group then would point out, this one would point in. Does that make sense? So the hydrogen bonding is done, not necessarily 90 degrees, but 109.5 degrees because it's tetrahedron from that. Does that help clarify a little bit?
So in beta,
Oh.
go ahead. Or I was gonna say, in beta sheets, R groups are connected to one another then?
R groups are connected to one another. What do you mean?
Like they're adjoining the beta sheets by the R groups? Or
Not necessarily. It depends. Once we get into tertiary structure, we'll see that a little bit more because these R groups that are pointing out, they may be facing another alpha helix, they may be facing a solvent, they may be facing another beta sheet. It depends on the overall surrounding structure. What was that?
I have like 3 questions that all go together. And on alpha helix, it's every 3.6
Yep.
amino acids that are bonded. Is it 3.6?
Hydrogen bonded, not bonded.
Yeah. Is it the same in a beta sheet? No?
Nope.
Okay.
So alpha helices have what we call more localized hydrogen bonding because it's every 1 beta sheets. This could be residue number 1, and this could be residue 211 or whatever.
Okay, so
So-
since they're this way, it's like different.
Right, so it could be, just because I have these two running here, it doesn't mean that this one runs and then it directly turns over to this. It could be that this beta sheet runs, comes way over here, does a bunch of things, whatever, and then the end of the protein ends here.
Okay.
So it's not necessarily super localized type. It can be, but it's not as localized as a alpha helix. It never will be.
And then, like, on the exam, would you say something like, write out like a 12 amino acid sequence or whatever, and then when it does turn, say it's for like an alpha helix, for the 4th one, would you want that to be like a proline or a glycine, or would it not matter?
At this point, we haven't gotten more into tertiary structure as to why it goes. Probably not, but
Okay. So as long as it's polar, non-polar, it matches up, it doesn't.
yep. So that remember that regular repeating structure. That's what the difference is between getting a beta sheet versus getting an alpha helix.
So the hydrogen bonding on this is just between hydrogen and oxygen?
Yep, it's still between that nitrogen, hydrogen, and this is the carbonyl oxygen. It's always, always, always. Remember, secondary structure is only interactions of the backbone. Okay? In the backbone, the only functional groups that we really have, well, we have the C alpha, that just has a hydrogen. The R groups are out because that's tertiary structure. The only functional groups remaining are the amine and the carbonyl. So those are the only two that we have.
And the same goes for an alpha helix?
What?
The same goes for an alpha helix?
Yep. That's not it. Yeah.
For like an amphipathic alpha helice, so it's like 1 in 4 is like yeah, but then I'm kind of confused on the order of that. So like 1 would be like non-polar, and then or polar, then 2 and 3 would be non-polar, and then 4 would be
Yep. So if you just follow kind of where you are here, if you're here, and this is like, let's say this is the solvent. Could you have an alpha helix if it's buried in the middle of a protein surrounded by all nonpolar residues? Could you have an entirely nonpolar alpha helix? Absolutely. But an amphipathic one has one face that's nonpolar, one face that's polar. And it depends on the orientation. Is it possible that you could have residue 1 here be polar and residue 4 here be polar? Yeah, and then 2 and 3 would have to be nonpolar for an amphipathic. Is it possible though you could have 1 and 4 be nonpolar and 2 and 3 be polar? Yes. They give the same
after that though, would it begin like a 1 again?
Yep, so it'd be 1, 2, 3, 4, 5, 6, 7, 8, you know, that type of thing. You'd have to just count to make sure that you have the right antipathic structure.
Okay, just, yeah, I guess. So like all of the ones outside would be a certain, like,
Yeah.
either polar or non-polar?
So, you know,
But
if you
then-
had something like this, if you kind of labeled it,
Yeah.
you can see, okay, 1, 4, you know, there's 3 between here, so it's 1 to 4. There's 3 between here, so if you just go, oh yeah, 1 would be, this would be, you know, N, G, G, N, G, G, N, G, G, or whatever, that's fine. Does that help clarify? Yeah, Travis.
Wouldn't at some point you have to have it not be non-polar because it's only 3.6 turns instead of a whole number?
Well, but it's 3.6, not because it actually individually lines up. Remember with the alpha helix, it's the N and the C and the carbonyl that line up from those residues. It's never going to shift to a new residue, like a 4th residue or a 5th, it's never going to shift over because the 3.6 doesn't go. The pitch is always 3.6 because you only have 3, and you can't have the C alpha on top of the C alpha. It's always going to be shifted over a 3rd.
I'm talking about amphipathic type deal. Wouldn't it start coiling around the alpha helix?
It may, but you never have an alpha helix that's long enough to do that.
Okay.
Unless you're making, and there have been people that do this, they've just made single, very long alpha helices that never change. But actually, people have tried to make ones that have been this long, and they've only been successful at making them this long. Because there's a certain toleration that we have. Yeah. Robin, and then, yeah.
Do the 1 and the 4 always have to be the same? Like you wrote like,
No, they can be different.
As long
But
as
for
the
an
same.
amphipathic, you'd have to make it that way. We're going to see in proteins, it might be that this piece all up here is all polar, this piece all down here is non-polar. That's more of an environment and tertiary structure that we haven't really gotten to protein folding yet.
so like as long as like the outside or the inside is all non-polar, they can be different non-polar, or do they be the same?
They can be different. I mean, it depends, right? If you have, you know, two helices coming together, and this part gets really close, and then it kind of spreads out, so there's a little more room. Here you probably might have glycines. Here you might have something maybe valines or isoleucines because it's a little bit bigger. So it depends more on that, on what kind of space you give to them as well. But you know, you don't have to be super creative or whatever. If you just say, you know, if you say N, G, G, N, that's fine with me. So I'm not looking for, does this really work in real life? It's just understanding the concept of what this is. Does that answer your question? Yeah. Tom.
When you say that people have tried to make alpha helices that are this long but only are this long, how many residues is that, or would that be about?
I'm trying to remember the paper. So this comes from a guy named Michael Hecht, who's at Princeton, and he's actually a theoretical biochemist. And what he does is he has a computer program that tells him, I want to make an alpha helix. So he uses exactly what you guys know about this. So he puts in a pattern that's about 1 to 4 type of thing to try to tolerate to make an alpha helix. And what he tried to do, I'm not going to remember the numbers, but I'll tell you what this paper did, is he wanted to make this monomer of an alpha helix that had another alpha helix around. So he wanted to make a dimer of 2 different helices coming together to make a coil. Okay? And he had it whatever size it was. But when they actually determined the structure of what it actually looked like, it was actually 2 dimers coming together. So that alpha helix that was double that length, it actually folded up on itself to make 2 of them and inserted with 2 more because it wouldn't tolerate being that long. So he's kind of like, wow, that was something that they didn't expect because they thought, well, an alpha helix is really stable. You can a really long alpha helix, should be super stable, right? But that's what you found is actually when you tried to make it that level or that length, it actually was like, nope, we're going to go split in half and make ourselves shorter.
And the whole thing was repeating all the way down? Or not necessarily?
It was similar in sequence. It had the same kind of repeating pattern, but not exactly the same exact amino acids. Yeah. But he has he calls it binary code, and his code is just either polar or non-polar, and that's it. So binary 2. And so he does repeats of, you know, just using polar, non-polar, doesn't care what the R group is, whether it's polar or non-polar, so doesn't care at all. Yeah. I can get you details on that later.